Hello, and welcome to this lesson on activation energy and its role in collision theory. In today's lesson, we will explain the concepts of activation energy and explore its role in determining whether a chemical reaction can occur according to collision theory. So far, we briefly looked at collision theory in the last unit. You have learned that for a reaction to occur, particles must collide with sufficient energy and proper orientation. Building on this foundation, today's lesson will help us understand how activation energy influences whether these collisions lead to a chemical reaction. This concept is crucial as it advances our understanding of how and why certain reactions happen, ultimately allowing us to predict and control chemical processes more effectively. Let's dive into the concept of activation energy and its role in collision theory. Firstly, think about particles in substances. These particles are constantly moving in random directions, and in doing so, they might collide with one another. This persistent motion and these collisions form the foundation of collision theory. According to collision theory, for a chemical reaction to occur, two key conditions must be met. 1. The reacting particles must collide with each other. 2. They must do so with sufficient energy. Activation energy is the minimum energy required for particles to react. Imagine particles as cars driving towards a hill. Just as cars need a certain speed to get over the hill, particles need enough energy to overcome an energy barrier, the activation energy. If particles don't have enough energy, they won't get over the barrier, and no reaction will occur, similar to cars that can't make it up the hill without enough speed. This concept is pivotal because only collisions where particles have enough energy to meet or exceed this activation energy will result in a reaction. If the energy is too low, the particles will simply bounce off one another without reacting. To visualize this process, we can use an energy profile diagram. This diagram tracks the energy changes that occur throughout a reaction. The x-axis represents the progress of the reaction. The y-axis represents the energy. In the diagram, the reactants are shown at the start and the products at the end. Between them is a peak, representing the activation energy barrier. The reactants must gain enough energy to reach the top of this peak before they can be transformed into products. The height of this peak determines how easy or difficult it is for the reaction to proceed. When a reaction has a higher activation energy, fewer particles have the necessary energy to react, slowing down the rate of reaction. On the other hand, lower activation energy means more particles can easily overcome the barrier, speeding up the reaction. When a reaction has a higher activation energy, fewer particles have the necessary energy to react, slowing down the rate of reaction. On the other hand, lower activation energy means more particles can easily overcome the barrier, speeding up the reaction. Imagine runners trying to clear a series of hurdles. If the hurdles are too high, only a few well-trained athletes will make it over each one, meaning the race progresses slowly. This is similar to a reaction with high activation energy. Only a small number of particles have enough energy to react. On the other hand, if the hurdles are low, more runners can easily clear them, speeding up the race. Similarly, a reaction with lower activation energy allows more particles to overcome the barrier and react, increasing the rate of the reaction. In today's lesson, we delved into the concept of activation energy and its significance in collision theory. We learned that for a chemical reaction to occur, particles must collide with enough energy, known as the activation energy. This activation energy acts as an energy barrier that particles must overcome for a reaction to proceed, similar to cars needing enough speed to get over a hill. Additionally, we looked at energy profile diagrams, which visualize the energy changes during a chemical reaction. These diagrams show the activation energy as a peak that reactants must reach to transform into products. We also learned that the higher the activation energy, the slower the reaction, and vice versa. Understanding activation energy helps us predict and control reaction rates, making it essential for chemists and industries relying on chemical processes. Watch the rest of the GCSE Chemistry course at Sophos Education.